So this has been a really good experience, especially since after COVID, it's nice to get more and more of this. So thank you so much. I know it's a lot of work. Right. So my talk is about, of course, in the spirit of the conference, I'm going to talk about holographic aspects. We are celebrating AdS CFT. And I want to emphasize that this is a sign of a little bit how the field has matured, that you can now go and look very specifically at some fairly subleading corrections. So that's what I'm going to be talking about, logarithmic corrections. And of course, I mean, this is, I'm going to talk a little bit about, some of it is my own work, and I will highlight it, but this is, I want to present essentially what the field as a whole has achieved in this direction. So many of this is, of course, the work of a lot of people. So it's clear that I don't need to motivate a lot the topic of entropy of black hole in this conference. As if anything, one explained in one of his talks, I think for the school, that this is like a very important stepping stone towards understanding the birth of the universe. But for us, or at least for me in particular, it's a really nice place to understand, to get to understand quantum gravity, quantum aspects of gravity, right? So if you see this formula is, of course, the Bekenstein-Hawking entropy formula, and it's loaded with interesting physics, thermodynamics, quantum gravity, etc. And that's essentially where we want to be. And but more importantly, for a theory of quantum gravity, this is really a nice bridge between macroscopic, so what your engine can do for you, and microscopic. So what we want for any theory of quantum gravity, any candidate should be able to produce this for us. So a microscopic, as a counting of degrees of freedom, a microscopic interpretation of this formula. This, of course, is one of the biggest achievements of string theory in the works of Strominger and Baffa and others in '96. So this was understood in a context. But what I want to tell you today is about a similar development, but of course in the context of AdS CFT. And this, of course, is what we are celebrating here. All right, so this is not, I need to. All right, so the topic, of course, is these logarithmic corrections. And I want to explain why this is what we want to do, this particular computation. And I will, so first of all, of course, the Bekenstein-Hawking is like many good formulas, they are a double sword formula. So they give you a very general result, but then you can get to that result by symmetry considerations, by things that have really nothing to do with the underlying degrees of freedom. So my favorite example from the gravity physics is the Bohr energy level. So when I was in high school, I was able to derive it, right, without knowing the Schrödinger equation or anything. You just think that the electron is some planet that moves around the sun, and then somebody tells you make the momentum quantize, and you get it. And that has nothing to do with the wave function of the electron or anything. So in gravity, we have a little bit of the same situation. We can get to this number, the 8 divided by 4g, by many different methods. But many of the methods really don't give you any information about what's behind. Now, this number here, and I will show it in this talk, this number here is really a one-loop effect. So it really tells you, I need to get this number correct, I need to know about things that are running in some loops, and that's really more dynamical than just understanding this number. So that's why this is a particularly interesting quantity to spend your time, all right? And as I said, what I will do in this talk is explain the collective achievement of computing this number, this coefficient here, on the gravity side as a macroscopic quantity, but also on the field theory side as a microscopic quantity. All right? Okay, so let me also, I will show you the computation because as physicists we believe a formula, a derivation is 1,000 words, right? But let me tell you that this quantity has a respective history in our field. So this coefficient, of course, as I will explain to you, is determined macroscopically only by the massless degrees of freedom. So you might have a very complicated UV completion of your gravity theory, but this number is completely determined by what you see, long-range fields, right? So that makes it a very, very good test. So if you come to me and tell me I have my theory of quantum gravity and it is better than your theory, I first check if you can reproduce this number. If you can do it, then okay, I take you seriously. Otherwise, this is a problem. And this is, as I said, this has been used in particular by Ashok Sen and many of his collaborators to very precisely scrutinize the Strominger-Vafa computation. There's a very interesting result there that hopefully I will touch upon today, which is the quantum entropy formula, how to compute these logarithms in those black holes. And we need to modify that formula a little bit in the context of AdS. It has also been understood or applied by Strominger and collaborators to see some microscopic realization of curve CFT. I believe Nikolai mentioned this beautiful example where you can check that the free energy of ABJM theory has this logarithmic correction in 11-dimensional supergravity. And of course, our goal here is to apply this setup to black holes. So here's my outline. So first, I'm going to talk about the topologically twisted index of 3D n equal 2 Chern-Simons matter theories. But of course, I'm interested not in the biggest leading term. I'm interested in this logarithmic term. And I am very happy that Nikolai gave a really good description with all the details. So when I show you an ugly formula, you will see immediately that that's a formula that you have already seen in Nikolai's talk. So then I will go into, this first part is going to be field theory. The second part will be the computation in gravity, but I will do it very generically for a large family of black holes. SE here is a Son-Sasaki-Einstein 7-dimensional manifold. So all these things live in 11-dimensional supergravity. And then I will tell you, or I will emphasize what we are learning, because of course you do a computation to learn something. So I will tell you some of the lessons that we draw from this computation. And now, if I have time, I will tell you about a similar story that is happening for n equal 4 super young mills. So this is the poster child of AdS-CFT, but in this context, it's a little harder to analyze, but there's some progress. And if I have time, I'll talk about it. All right, so any question or any comment at this point, just to get into a nice pace. All right. So here's ABJM theory, right? So I hope that you remember part of it from Nikolai's talk. So there are two gauge groups, UN and UN, and these are Chern-Simons matter theories, so they have level K and minus K. What I like about this, and what is important, one really qualitatively better story that we have in AdS-CFT is that I can tell a condensed matter person about Chern-Simons matters and no eyebrows go up, right? This computation, when Strominger and Vafa did it, required deep brain technology, moduli space of instanton, and that makes it that makes it a little bit more mysterious for the broader audience. But here we're talking about vanilla style quantum field theory. So that's really one useful thing. And again, there's a lot of decoration for this theory, supersymmetric. It has all the symmetry, but I will not go into those details. The important thing is that we can do some very interesting calculations in this theory. In particular, we can compute the topologically twisted index. So this is, again, a partition function e to the minus beta h. So that if you are part of the school, that's the main message. So I'm counting, this is my Hamiltonian interpretation. But of course, I have to do it in a supersymmetric way. So I count bosons and fermions with sign. And then I can decorate further with some other chemical potentials that will correspond to some global charges that we have. All right, so this is a partition function that counts half BPS states that are annihilated by this supercharge, which I enter here in the Hamiltonian. Now, in the Lagrangian formulation, because of course this is a nice formula, but maybe not very easy to enumerate all the states that way. But what we can do is to use Lagrangian formulation, and then this formula is going to be computed by the path integral on this space, S1 cross S2, with some topological twist along S2. And again, I'm thankful that all this was introduced in talks not only by Nikolai, but also Dario, etc. Okay, this is a fairly standard story in the field. Now, here is one ugly formula that maybe yes, maybe not, but you might remember from Nikolai's talk. So this is the evaluation of the index. There, if you remember, there was some issues no, but some path that you take in some contours and you evaluate at the poles, etc. What I want to emphasize, since we have a broad audience here, is that this we call the Bethe-Ansatz equation, and this is very similar to what Kostya was showing. But so far, we have not made a lot of progress in that direction, interpreting this. So what we do is we have this problem. It's an algebraic problem of 2n by 2n variables, and you can just solve it, right? So let me, oops. So this is another way to write this Bethe-Ansatz equation. I will not, this is not really so important. The important thing is that how to evaluate, here's my prescription. So I solve this equation, and I can solve them numerically very, very precisely, right? Maybe not as precise as has been done right now, but at the time when we did it, it was sufficient for us. I can solve this equation. I insert into the expression the ugly expression of the previous page, and I get my topologically twisted index exactly in n, right? So then I can, of course, do numerics and try to extrapolate. I take large n, and I have very good collaborators who can. I had a table and everything, but I think this is enough to convince you that, of course, this is the leading piece. This is the part that will guarantee, and this was done by Benini, Christoph, and Zaffaroni in 2015, a very beautiful result. So this answer, when Legendre transform and taking some extremization, gives you precisely the entropy of the dual black hole. But here I'm interested in going down the line to this term, the logarithmic term. So I have this term. This term is the field theory prediction for what the log correction to the entropy should be. And you can do, yes? So this is the term, good. So the leading, this is large n, so you can think of this formula best in the large n limit. So n to the 3/2 is the leading contribution that corresponds to the Bekenstein-Hawking entropy. Then there are other contributions that I don't talk about in this talk, and then I keep going. But I have done this very precisely, so I'm very, very confident in this number. That's all. Yes? This expression, this is exactly in n. So I can compute for n equal 2, 3 for any n. But I want to connect with gravity, so I want to push this computation as far as I can to be sure that I'm in the comparing with the supergravity regime. Okay. Any other question? Good. So these equations, they have one particular type of solution that grows with n, and that's what we use. There might be other solutions, but there might be other solutions, but this is the one that grows with n and that contributes to this computation. Right. So So in this context of 3 dimensions, it's not very clear because they don't scale with n. Now, for n equal 4, there's a beautiful story where you might have many solutions, all scale n squared, and then you have to interpret what they mean. But here, it's just one type gives you n to the 3/2, and the other gives you very subleading contribution. Yes, this corresponds to sorry, this F1 here. I didn't write it, but in Nikolai's talk, this is very, very now better, much better understood. And this, of course, comes from higher curvature corrections. On the field theory, sorry. This is leading planar. This is the lead, yes. Okay, but I want to remind you that this planarity with this theory is a little complicated. One, yeah. Yeah. Right. Yeah. All right. Good. There's an. Yeah. 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 Yes. All right, so let me emphasize here first. So we can extend similar computations for many of the quivers, and I also answered the question. So there are many quivers that look different, but if you do this computation, they actually also give you the same result. All right, so that was the field theory side of this class of three-dimensional Chern-Simon matter theory. Now I switch to the gravity side. So in the gravity side, these theories are described by a stack of N2 branes, probing for ABGM in particular this singularity, and the configuration that I'm interested that corresponds to the topologically twisted ABGM is of course a gravity theory with some magnetic charges, and that's the dictionary. And so here I'm going. So here's the solution from the four-dimensional point of view, but of course my treatment is going to be intrinsically 11-dimensional. So here's the metric. You can see that for large R, this is AdS4, and then there's some decoration. What is important is that you have this black hole in AdS4, then you have your magnetic flux here, and this can be embedded in 11 dimension. So I wanted to flash very briefly the entropy so that you see this is a highly non-trivial function of the magnetic flux, and this precise combination is matched by the prescription that I explained before. So this is just by seeing how the leading order matching is by no means trivial. All right, so good. Now what we want to do is to compute quantum corrections around this solution, right? And compute the coefficient of the log, and then compare with the coefficient that we have already computed on the field theory side. So because I want to address, in a few slides, I want to address young people in the audience, especially I want to be a little bit more precise. Also because when you talk about a quantum computation in gravity, you should be immediately suspicious. Oh, gravity is non-renormalizable. If you're not doing your computation in string theory, what are you doing? So I want to convince you that in all this, all that is true, but there's one thing that you can extract cleanly from quantum supergravity, and it's this coefficient of the log. So I want to really make clear that this is one of the few things that you can really do and be confident. So I'll show you a few steps, all right? So because we want to compute fluctuations around the black hole, around this background solution, what I end up doing is essentially looking at determinants, right? So when I integrate these fluctuations, quadratic fluctuations, I need to evaluate some determinants. The way to evaluate the determinant, one prescription, of course, is to say, well, the log of the determinant is the log of the sum of the logs of eigenvalues, but I don't want the zero eigenvalue here because it will create a lot of problem, give me zero. So I have to treat zero modes separately. Now, in this context of curved space, the best way to do this is to use the Higgs kernel, the Higgs kernel, which I formally write like this. So these are the eigenvalues or eigenstates of this operator, and these are its eigenvalues. Now, I'm interested in the log of determinant without zero modes, but the Higgs kernel counts the zero modes. So what I need to do is, this would be the expression for the determinant. I have to subtract the zero mode, and that would be my answer. All right, and now, a very important fact. Under very general conditions, these operators admit, or the Higgs kernel admits the Seeley-DeWitt expansion. So you can think of this as expansion. You see the first term, n equals 0, is t to the minus d over 2. This is a square root. This is a Gaussian integral. So this is, you're very close to flat space. All momenta are sort of Gaussian variables. You integrate them, you get the first term. But there's an expansion. That expansion has been discussed a long time in the math literature. The important thing is that we know this for sure. And we know these coefficients, they are combinations and contraction of Riemann tensors. All right, so my computation becomes, I can control it with this expansion. Now, because I'm interested in the log, so this is the important thing. I put it in my, just bear with me because I think it's worth it walking out with, okay, at least one good piece of physics. So when I plug this in my definition of determinant, I see many contributions. This is in general a very complicated story. But if I am looking for log, so of course I rescale this because the operators are, if I have a kinetic operator, it scales as 1 over length squared. So I can see that to get log, I need only one term in this expansion, which is the one in which n is d over 2. So there's only one term in the expansion that affects the log. Nothing else can touch the log. And more importantly, when I compute this, you see the cutoff enters. So how complicated my theory becomes at higher dimensions is in the cutoff. And that would be, of course, something that I don't have a lot of control, but the coefficient cannot be affected by shifting the cutoff or anything else. So this is a very clean object in the sense that of all the information that is there in the determinant of the operator, I only need in its expansion this coefficient. All right. Now, on very general grounds, I cannot construct this non-trivially for spaces that are odd dimensional. And remember that we live in 11-dimensional supergravity. So let me summarize what I just walked you through. So first of all, the coefficient of the log is very robust. It's independent of that cutoff. All the information that I need is encoded in this AD divided by 2, which is 0 in odd dimensions. So the only thing that I really have to worry about, okay, I can compute my partition function and the entropy using thermodynamics, but the only thing that I really need to worry about is the 0 mode. So let's see what happens now concretely for 11-dimensional supergravity. All right, so for 11-dimensional supergravity, my quantum theory has a graviton and a 3-form field. So its partition function would be like this. There's no other contribution. There's no silly DeWitt coefficient in 11 dimensions. So I need to subtract the 0 mode, as I show you in the Higgs kernel expansion, but I need to add them back with the appropriate scaling of that 0 mode. So that's all I need to do. And then, of course, I might have Gauss, etc. Gauss contribution is separately. Now, there are no 0 modes in the graviton in 11 dimensions around this background. So I only need to really worry about quantizing a p-form. So this is general for a p-form. We are interested in the 3-form of 11-dimensional supergravity. So this is a very beautiful paper by Siegel in the 80s. It's called Ghost of Ghost or something like that. But essentially, if you have a p-form, right, and you want to do a quantum theory, you need to fix some gauge. But that would be a p-1 form. But that in itself has some ambiguity in a p-2 and so on and so forth. So you have to keep going down until you finish. And essentially, and after that, this is how you should consider all these p-forms that you needed for the quantization of the original form. So here's the summary. For the 3-form, I need to introduce 2 2-form ghosts that are Grassmann odd, and then 3 1-form ghosts that are Grassmann even, and 4 scalars that are Grassmann odd. That's the summary of that prescription. Now, this 3-form itself can be decomposed as a massless 2-form in the black hole. The black hole does have a 2-form 0 mode, and a 1-form in the compact dimensions, S7. But S7 does not emit trivial 1 cycle, so the only thing that contributes are the 2-form, because that's the only 0 mode that really remains in this background. So here's, again, very briefly, what Siegel tells me to add if I am quantizing a 2-form. Again, this 2-form was needed for quantizing the 3-form of 11-dimensional supergravity. And the beta, how to add it to the path integral, comes by considering the fact that I want the measure to be normalized correctly, so it gives me the scaling that this field contributes, so I put everything together. So I'm here doing a slightly more general computation where my black hole has an arbitrary Riemann surface, so that's why this G is appearing here, but this is the answer, which I can put in my thermodynamic formula, and I obtain precisely the formula that I had in field theory, okay? So importantly, I had to really know about these quantum fields that were that were important on one loop, and only a two-form zero mode contributed. Yeah. Yes. So 1/2 I take G equals 0 because there I just wrote it for the sphere. But that computation, exactly as we did, I can do for any Riemann surface, and then I will have 1 minus G here. Sorry? The fermions don't emit zero modes in this background. There are other backgrounds where they do, and that's yeah. All right. Yes. Please. Yeah. Yes. Yeah. So I have a slightly different computation where I include that, but not. Okay. Maybe I'll. Okay. Okay. I have to be a little bit more careful, but that you're saying then I will find a three-form zero mode in AdS4. One. Okay. Okay, but yeah, this I don't see in this computation, but I would consider situations where I do have one cycle in the Sasaki-Einstein 7, and no, actually there's no. Well, okay, there's another model that I might discuss in which I generalize this, and it also agrees. All right. Yeah, and similarly for all these Sasaki-Einstein, you have, there's a theorem that the first Betti number has to vanish, so this result clarifies the entropy for all the quivers that I show you at the intermediate step. All right. Okay, so there's another kind of AdS4 black holes, and this you make by, instead of an M2 brane, they come from an M5 brane. And here, this table is part of the AdS-CFT dictionary. So what really matters is the scaling is different. So you have to consider that scaling to match the gravity and the field theory side. And this is work that I did with Don Mengan, Nagwu Kim, and also another paper with Benini, where we find complete agreement. Now, this B1 is the Betti number because this hyperbolic three-manifold might have one-form zero modes, and then they will match. So actually, I think I have time. I can show you the computation here. So this is what I showed you before. Okay, the difference is because the scaling with L is different. But now, if I have non-trivial one cycles on this hyperbolic three-manifold, they really contribute. I can have my three-form zero modes that come from the, okay. Part of them are the number of three-form zero modes come from the two-form zero mode times how many one-form zero modes, and you can see that putting this together give me this result. So I don't show you the field theory computation, but the field theory computation is something that can also be done using 3D duality. Okay, I will not just, okay. But there's this agreement. All right, so life is good, right? So the story that I have told you is a story of success. But there are subtleties, especially from the conceptual point of view. We had, in fact, this was not the first computation that we did. The first computation that we did, we follow Sen's quantum entropy formula. So very, very briefly, the classical entropy formula of Sen is a prescription for how to include higher curvature corrections to the entropy by going to the near horizon and analyzing the theory there. But, and of course, it works perfectly in all black holes. That's one. Now, the quantum entropy formula also was very successful in asymptotically flat black holes, and it tells you, go to the near horizon, do your computation. But actually, that which was the first thing that we did, actually leads you to a different result. So here's the computation. It's a little bit complicated, but I can maybe very briefly mention the key points. So if I go to the near horizon, these things are going to be AdS2 times M9, and M9 would be some S2 bundle over S7. But you have all the information to do the computation. Now they're really, in AdS2, you have, of course, graviton zero modes, fermion zero mode. So it's a lot more complicated, and here's the list of all the modes and how they contribute. And the answer does not agree with the field theory answer, all right? And this near horizon result was something was done also by Intak John and Lal, and same answer, but it does not agree. And now what we understand, and this is one of the lessons that I advertised at the beginning, is that if you want to understand the quantum entropy formula, so the quantum entropy formula really counts near horizon degrees of freedom, but in AdS, you might have zero modes that are really not localized near the horizon. And these are global modes that you need to include if you want to have agreement with field theory. Now, of course, in AdS5, where there's some theorems about odd-dimensional AdS5 and absence of zero mode, so you might do something better in the sense that you don't have this problem. So let me emphasize a little bit more the importance of this computation here. So with my former student Marina and postdoc Victor Golet, and this is not my colleague Jim Liu, this was an undergrad in Michigan. We study very, very generically AdS4 black holes in minimal n equal 2 gauge supergravity. And the idea was to compare the full computation of the black hole with its near horizon. Now, what we find is, of course, that this computation, so there's heat kernel involved. It's a little, it's convoluted, but the important thing is that for a stream of black holes, it really does not matter the part that comes from the, let me call it dynamical part. From the heat kernel, you can really go all the way to the near horizon and evaluate it, and you get the same answer. But of course, this computation really misses zero modes, and that's why the quantum entropy formula of SEN in AdS needs to be corrected by these zero modes. And of course, a posteriori, it makes sense, right? So there were some talks about condensed matter in AdS-CFT, and a lot of the reason why there's interest in condensed matter in the AdS-CFT is because precisely we have hairy modes outside the horizon, and this is, of course, the idea that behind the holographic superconductor and everything. So in general, we know about this, but here we can really concretely use for counting very precisely. All right, so good. So how much time? Okay, good. So then I can tell you the second part of this story. Now, what I told you was mostly about this spherically symmetric, magnetically charged black hole, right? So they are interesting, but of course, rotating black holes are a lot more fun, and they are the ones in the sky that are certainly rotating. So you want to be able to have something realistic in mind. Now, for rotating electrically charged black holes in AdS4, 5, 6, and 7, there was this beautiful set of work, and that is here, that explained the microscopic entropy of these black holes using the SuperConformal Index. So this is a really painful sort of story because it was not well understood at the beginning, and it really required some nice insight that was provided, again, mostly in this in the approach of Cabo-Bisset, Casani, Martelli, and Murti. But now this was understood, and this same sort of philosophy was applied to AdS4 black holes, to AdS6, and to AdS7. In every case, there was perfect match between the Bekenstein-Hawking entropy, again, the big chunk in the entropy, and the SuperConformal Index at leading order. Now, yeah, you can pat yourself in the back. So string theory is doing interesting stuff, right? So you can match this. But you should also ask, so do we really need the full UV complete theory to answer the question of entropy? After all, right? So we believe that maybe at least the bigger chunk we should be able to get by some symmetry, low energy configuration. So okay, it's nice that you can do it, but maybe you're killing a burst with a cannon or something like that, right? Maybe there's a simpler set of assumptions that will give you a similar result. So this is the direction I want to go, and this is where my work my most recent work is going. But again, I want to, the similarity with the Strominger-Buffa era is that, of course, first you use deep brain technology, instant top moduli space, but then you realize that, well, near the horizon, this looks like AdS3. There's this beautiful formula of Brown and Henault. I can also explain it, right? So maybe not in full detail, but this is important. And I think that the analog of that part has been missing a little bit in our AdS-CFT context. So that's where I want to go. But before that, let me tell you about the SuperConformal Index. So again, it's always, this is a Hamiltonian, right? A partition function with supersymmetry. And now I have two angular momenta, J1 and J2. So these are their corresponding fugacities. And I have some extra global charges. This is, of course, the Hamiltonian presentation. And you can evaluate it using path integral. And you can evaluate. This one in particular, actually, this is nice because this one you can evaluate also in the Hamiltonian approximation. You can really count the states, put together, and you will get this object. So this is actually a little nicer than some other partition function. Like, for example, the SuperConformal Index in 3D has some non-perturbative sectors, and it makes it very obscure how to get it perturbatively, but here we have no obstruction. So this is a very well-defined object. You can compute very precisely. All right, so what I did with my former student, Alfredo, and this is now my colleague, Jim Liu, and postdoc now in Leuven, Jung Ho, was to really carefully study the SuperConformal Index. We studied it in two different approximations, two different even methods to study. But after, I will not bore you with the details, but I haven't read here. I am like the logarithmic police. So wherever there's a problem, I go and I investigate. So if who's the culprit, right? So I go into the SuperConformal Index and I check this number, and I compute it very carefully in different ways. And so I'm very sure that, yes, this is the signature of the SuperConformal Index. This number, of course, we did it using different techniques, but then other groups reproduce it, so that makes you feel like, okay, this is great. And then there was recently, I actually have to apologize here. Ardehali and Samir Murthy also simultaneously have the same analysis. You can obtain the SuperConformal Index, as I said, is so nice that it has a perturbative interpretation, and then you can also have an effective field theory interpretation of really reducing four-dimensional fields to 3 dimensions, and then you end up with a nice Chen-Simon action. So this was also understood, and this number was interpreted now as a degeneracy of vacua in the 3D theory. So it's super robust, even in field theory. And of course, what we would like to do is to match it with gravity. So to match it with gravity, let me cut to the chase. So if I now have to study type 2B supergravity in 10 dimensions, if you look at the Higgs kernel of fields in 10 dimensions, it's 2 pages. So I have tried, but it's still work in progress. So I tell you about a shortcut that is also connected with the philosophy of go to lower dimensional gravity and see what it can do for you. All right. So I told you in the previous 2 slides about this line here. Well, at least about the story here. But you can take a limit, near horizon limit. It's called Bardeen-Horowitz. And then you get something that is complicated, but it's locally AdS3. So here you can see AdS2, and then NS1 fiber of AdS2. So you say, almost AdS3, but not quite. So there's these functions here that mess up. But the important thing is that these kind of backgrounds were studied a long time ago by Strominger collaborators. And you can check that there's a set of prescription that will give you the entropy correctly. So this curve CFT is something that we need to understand better, but at the moment it's a recipe. Do A, B, and C, and you will get a microscopic description of this geometry. And of course, with my ex-student Marina and postdoc Junyan, we applied to all these black holes, same recipe, same result. So you can explain the entropy of all electrically charged rotating black holes in AdS 4, 5, 6, and 7 by going to the near horizon and applying curve CFT. All right, so now here's the picture of what I said in words. Focus on this near horizon region and try to do as much as you can. So in the previous slide, I told you that we get the Bekenstein-Hawking entropy, the big leading piece. But I now will tell you that because the curve CFT gives me a central charge and it gives me a set of global charges, and I know how two-dimensional partition functions behave, I can read the number of the density of a state by doing a Laplace transform. And of course, the saddle point in this computation gives me the leading entropy, but I can also go to, let's say, Gaussian approximation of this process and get a correction. This correction, now, okay, so you might think, oh, you got -2, so this is not the log that you have before. But it is the log that I have before, only that when I go from one ensemble to another, I get extra contribution of logs. So this is a perfect match. Now, it's not at the level of what I told you for the AdS4 black hole. In the AdS4 black hole, I had the field theory computation and the supergravity computation. So here, I'm not doing that. As I said, I'm having trouble with the 10D computation. But what I have shown is that I go to the near horizon. There's curve CFT. I can push curve CFT to one loop, and it still gives me the right answer. And of course, I put together my first part with my second part. And what happens is that in AdS5, there are no zero modes. So I have no obstruction going to the near horizon and doing my computation there. And this is what I find here. So with that, I come to my outlook. So I told you a little bit about some lessons in AdS4 versus AdS5. So now we can try to understand how more carefully to treat the quantum entropy formula, how to compute the quantum entropy of AdS black holes. So zero modes are an obstruction, so you have to be careful with them. The degrees of freedom by the computations that I show you and other work that I mentioned but did not discuss, the degrees of freedom do not really live locally. So there are global degrees of freedom in this computation that you have to be very careful. Unfortunately, in this talk, I cannot tell you much about the type 2B computation of this log of n for AdS5 black hole. I only told you a lower dimensional interpretation. But I think other avenues open, and in particular, the curve CFT, which is thus far have been a sort of obscure prescription that if you apply, you get the right answer. Now, by putting it embedded in AdS D+1 CFTD, I have a better chance to understand, okay, this is what happened. I have my field theory, and I took this limit. I tried to mimic what I did in the gravity side in field theory. So I think this might be a clarifying venue. I plan to explore that. More importantly, and this is, again, some other ongoing work, so by going to the near horizon, you can try to study aspects of black holes that are not restricted by supersymmetry. All the partition functions that we compute in CFT4, CFT3, they are very rigid. You can compute them in supersymmetry, but if I tell you, okay, give me the answer that is a little bit away from extremality, that there's nothing you can do. But if you go to lower dimensions, you can do it. And we have, so one goal is to apply a lot of new results that people obtain in JT gravity, SYK, that kind of analysis for this bona fide AdS CFT black hole. I think that will bring that story into a firmer ground. And again, I think that most importantly, we know that by definition, right? By definition, we have a gravity theory dual to a field theory. Field theory is unitary, end of the story, right? So you can say that this is the end of many of the puzzles we have dealt with in gravity, but now we have a concrete playground, a concrete set of models where we can really see the details. Look under the hood and see, this is how Hawking radiation really is unitary. So thank you very much.
Questions for Leo? Okay. Okay, let's start. Kostas, Johanna. Yeah.
Yeah, I have two questions about the curve CFT part. So in curve CFT, there was a whole issue about boundary conditions, and it looked kind of, the boundary conditions were chosen so that we get the result that we want. Yes. Do you have a better understanding of the boundary conditions now that you have embedded it in many different cases?
I have a slightly better, but I mean, this is something I'm working on. But the idea is, of course, to try to understand the boundary conditions as boundary conditions that come from a higher dimensional CFT. And so we are not completely done, but I think this will clarify. I'm with you in your suspicions of curve CFT, but I think that this is a way that one can really understand it in a solid ground. But okay, the short answer is I don't yet have a clean understanding, but I see that there were directions that were taken that are not compatible with what we do from higher dimensional CFT.
And then the related question is, now that you have examples where we have both standard AdS CFT and KER CFT, do you understand the relation of the CFT in KER CFT and the higher dimensional CFT?
We partially understand a little better the CFT that comes as a subsector of the higher dimensional CFT. But for example, this thing about the fact that KER CFT was supposed to be dual to a chiral CFT, that seems to not be very clear in this picture. That's not what we see.
So you mentioned, well, here you mentioned SYK, and previously you also mentioned the fact that the hair is relevant for the condensed matter applications of.
Yes.
So if you think of your subleading terms, these logarithm terms, do you see what application would they have in the field theory side? Is there anything you can say about that?
From the lower dimensional field theory point of view?
Yeah.
Good. So yeah, so at the moment the goal number 0, and so there was a nice paper by Francesco and collaborators in December that took for the topologically twisted theory, reduced to a one-dimensional theory, and wrote something. So that's the model that you need to study and see. And we're trying to do the same thing in a slightly different model. Of course, I like n = 4. I told you because perturbatively is nice and there's no non-perturbative sector. So, but we are studying this. We're trying to see. Well, one thing I can talk to you separately, but we are seeing that some of the structures in n = 4 are already explaining this idea of averaging and randomness. It's not really random, but it's mimicked by something random. So that we can now see from n = 4.
Okay, excellent. Thanks.
Thanks. Somewhat very naive outsider question, but if you go to the Schwarzschild case, do you expect logarithmic corrections on a Rindler space, so logarithmic corrections to the Unruh effect to be completely different, or is it going to be the equivalence principle will be maintained with these logarithmic
Okay, so good, thanks. So I have not thought about Rindler much, but so in my first slide, let's see how to go home here. Okay, I will not torture you going back through slides, but in the first slide I mentioned, maybe I didn't say, but I wrote it, that Ashok Sen has computed log corrections for Schwarzschild, and then he used that to say, well, here's what Schwarzschild says, and I told you the litmus test. So if you have a UV theory that claims to explain Schwarzschild, you have to get this number. And he, I think, applied that to loop quantum gravity. So and it doesn't seem to reproduce the number that is Schwarzschild. So this is this is the way that we can tell if your UV theory is really compatible with what it should be. Now for Rindler, I expect there would be a similar story, but I have not looked carefully into that.
Okay. Yeah, I was just going to ask, we had these accelerating black holes in 4 dimensions too. Do you know off the top of your head what the answer would be for the log correction in that case?
No, unfortunately I don't. But I'd be happy to take a look. As I said, I'm a surgeon in the log police.
Right. So
log police department.
It was 1 minus the genus, so that looks like it's going to be the Euler number, the orbifold type Euler number, for which there's a clean answer.
I see.
So that would be the natural guess.
Okay.
Also, the large N index has not been done yet, but someone will do it eventually and look at the log.
But I thought your paper, you have an upcoming paper about the index of for the.
Maybe I can clarify.
For the
spindle. We have a paper with the index for the spindle, and therefore that's the index relevant for these accelerating black holes. And we are now starting to look at the large N, which is a is a different kind of calculation, as you know. It's a bit more complicated because the starting point that we already published is more complicated. But I had an easier question, if I may, related to the to the AdS5 black hole computation that you said that in type 2b it's very complicated. did you try, or could you try looking at the heat kernel computation in 5 dimensions and then get some mileage from there?
Right.
Like you did for the 4-dimensional case, but then taking into account the 0 mode somehow.
Yeah, so this is a very tricky situation for this log. So there's it doesn't commute, right? So in 10 dimensions, right. So the heat kernel business is very subtle in that sense. So the product of determine, if you have a space that is product, is clearly the heat kernel is not just simply the product. So there's some more complicated combinations. So that's why if I do it in AdS5 and I get the wrong answer, then I don't know. I don't learn much. So that's what I'm trying insisting on 10 dimensions, because if I'm guaranteed to get something that is meaningful, and if it matches or not, then I have to really think. But yeah, so that's right. In odd dimensions, I would be trying to look for 0 mode. So I got a nice hint from these papers, again, that did the effective field theory, because they interpret this number as some one-form symmetry that gets broken, and I'm trying to see if that one-form symmetry is really in the B field. So there's some information, but I think that the 5-dimensional point of view is too dangerous in that sense.
I had a kind of immediate comment top of my head, but maybe we can discuss it later. I think some of these black holes can be uplifted to 11 dimensions as well, can be embedded. These 5-dimensional black holes can be also embedded in 11 dimensions.
Oh, that would be wonderful. Yeah, that would be great. I definitely want to hear more about that.
That could be useful.
Yeah, thanks.
Any more questions or comments for there we go. Okay, let's go with Andrea first, and then I'll go there. Yeah.
Thank you. It looks like these log n terms do not depend on the details, like on which field theory you are studying, or if you wish on what is the specific Sasaki-Einstein in the internal geometry. Can you comment on why that's the case?
Yeah. So yeah, maybe I'll this is the part that I take as a educational part. So I try to torture students through this computation because as I said, I think it's very instructive. So maybe here. So if you look at these numbers, right, and the particular number that is useful for this computation, this 8d/2, these are really the wild anomalies that appears in field theory. So this number, again, the computation, I never mentioned anomaly, but the fact that the answer is very robust. It's like anomalies, we know they are one-loop protected, etc. So this is the flavor that you should attach to this number. This number is some sort of anomaly that comes with the set of fields that you have, or of course, the background. But that's for me, is the cleanest way to see the nature of this term. So it's kind of, yeah, very close to being an anomaly in that sense.
Okay, thank you.
I have a naive question. What is the origin of logarithmic correction to the black hole entropy if we think from the point of view of 11-dimensional supergravity action point of view or some other supergravity action? For example, if we want to compute the higher derivative correction to the black hole entropy, then there are terms in the action like R square, RQ, or some other higher curvature term, and we can compute the correction using world entropy formula. So what is the terms in the action from similar to the higher derivative term in the action here?
Right. So good question. So what I told you here is so what you're saying is what should change is really the nature of this. What is your quadratic fluctuation? So now instead of just having Laplacian, you will have a more complicated story. But that's how I will consider. Now there's also, I mean, normally it's a standard in the literature that you sort of, if you have a black hole, and then you want to look at corrections to the Bekenstein-Hawking entropy, you sort of separate. You said, okay, there are corrections that come from higher derivative, and they can be powers of the area, square root of the area. They can be like that. They come from higher derivative term. Yeah. And then there's this log that comes only from, as I said, massless fields in the loop. So in that sense, it's a little bit like two different directions.
Oh, Is it like a log L? Because you are computing this from log L term. L is like some length scale.
No, L is on length scale, so yeah. But those are different. Those are different.
Okay.
Okay.
Thank you.
Yeah, sure.
Any more for Leo? Anyone else? No? Okay. Horacio, when we come back? Before we clap. What? 25, 11:20. 11:20 we have to be here, okay? Clap, clap. Thanks very much.
Okay, thanks.